In this video, we're going to talk about radical notation and simplifying down radicals. So a radical, again, kind of the most basic example probably everybody is used to seeing, is a square root. So suppose I'm trying to find the square root of 25. Again, they don't write it, but it's understood there's a little index here of 2. And whatever this number up here is, it basically means you need a number multiplied by itself that many times, in this case 2 times, so that we get the number 25 back. And I need the exact same number inside of here. And notice that 5 times 5 equals 25, and that is going to be the solution to this problem. It says the square root of 25 is 5. Now notice also that negative 5 times negative 5 would give you positive 25, but the way that we just define square roots or any even-powered root is we only want to use the positive solution. So even though negative 5 times negative 5 is 25, we would never say that the square root of 25 is negative 5. We just use that positive version. So another example here of this idea. Suppose we have the cube root of 8. Okay, so in this case it says I need a number multiplied by itself 3 times so that I get positive 8. Well, again, notice that 2 times 2 times 2 is positive 8, so we say that the cube root of 8 equals 2. If we had the cube root of negative 8, what would the solution to that be? Well, in this case, we can have a negative number as a solution because I need the number that I get out to be negative, and if I multiply a number by itself 3 times, the only one that's going to give me a negative out is going to be if that number is negative. And notice negative 2 times negative 2 times negative 2 does give me a negative 8. So the cube root of negative 8 is negative 2. Suppose I wanted the square root of negative 25. Well, in this case, I need a number that's multiplied by itself twice that gives me a negative number. Well, if it's a positive times a positive, I'm certainly not going to get a negative. But notice also, if it's a negative times a negative, I'm not going to get a positive. So we would say the square root of negative 25 has no solution. And some of you out there may be saying, well, what about imaginary numbers? Okay, there are something called imaginary numbers where you can have solutions for these types of equations, but probably not going to see those in most math classes. They'll kind of teach them, but then you really don't even use them that much in most of your classes, so we're just going to leave those out for now. Alright, let's do a couple others here. Suppose I have something like, so now this is going to be an example of simplifying a radical. Suppose I have the square root of 8. Well, can you think of a number multiplied by itself that gives you positive 8? Well, 2 times 2 is 4, 3 times 3 is 9, so I know this number is going to be something between 2 and 3, but it doesn't seem like there's a nice positive whole number that's going to do it for me. What you do in this case is you factor the number underneath, so notice I can write 8 as 2 times 4, and the idea is, again, I'm taking square roots here. If there's a number underneath here that you can take the square root of, then take the square root of it and you can pull it out front of the radical. So notice in this case 4 does have a square root, and I'm going to pull that out front. The square root of 4 is 2, and then I'm still left with my original square root of 2. He's still hanging out underneath. And this would now be considered sort of the simplified version of square root of 8. Maybe let's do one a little harder. Suppose I have the cube root of 40. So again, you may play with this and think, are there any numbers multiplied by itself 3 times that give you 40? And I certainly can't think of any. So, 2 ways you could go about doing this. First, suppose I wrote 40 as, so it's definitely 5 will go into that, and suppose I wrote it as 5 times 8. Well, again, now I'm recognizing that 8 does have a cube root. The cube root of 8 is 2, so I'll pull that number again out front. And I'm still left with the cube root of 5 underneath. And I can't really break 5 down any further, so this would be the simplified version. And another way to do these problems, so suppose I have the cube root of 40, so same problem. Suppose I didn't make the factorization as 5 times 8. Suppose instead I said, well, 40's even, so I'm going to write that as 2 times 20. Well, I don't think I can take a cube root of either of those numbers, but this is where I can keep factoring. So 2 doesn't factor down, but notice 20, I can write that as 2 times 10. So there's my original 20. And again, I can't factor this down any further. Well, at least not the 2 and the 2. The 10 I can certainly factor down. So here are my 2 original 2's. If I now break the 10 down, I'll get 2 times 5. And now everything, I've got a prime factorization of the number 40. And if you've forgotten how to factor, definitely take a look at one of my videos. I definitely have some examples of factoring numbers down. But you can't take a cube root of any of these numbers. But the trick is, if you look at, again, the index of this radical, which is a 3, if you see a number underneath the radical sign that number of times, so I see a 2 times 2 times 2, I see a triple of 2, you can pull it out front of the radical exactly 1 time. So it says you need 3 of them. Okay, I've got 3 of them, and I can pull it outside 1 time. And again, I'll get 2 times the cube root of 5, which is what I got up here in my other example. So it's not like if you factor things in a weird way that you'll get a different answer. So that's just one thing to be aware of. Okay, so this is the basic idea of how you can simplify down a radical. Let's talk about radicals and exponential notation here a little bit. We're not talking about multiplication on radicals just yet. You know, you can multiply things under square roots. We won't worry about that just now. Okay, there's a relationship between radical notation and exponential notation. So suppose I have a number a raised to the b power, and the index outside is a c. The idea is you can write this as a fractional exponent as a raised to the b divided by c power. So, and obviously you can go either way. So suppose somebody said evaluate 8 raised to the 1/3 power. Well, I could rewrite this as 8, that's the number that goes underneath. Whatever part, the top part of the fraction goes underneath, so I'll get 8 to the first, and then a 3 outside. So really it just says I'm taking the cube root of 8, and we saw from an earlier example that the cube root of 8 is 2. So 8 to the 1/3 is really just a fancy way for writing the number 2. Suppose I have 8 raised to the 2/3. Okay, so there's two ways you could do this one. Again, I could rewrite this as 8 raised to the 2nd power cubed. And you could either multiply this out immediately and start, basically thinking about the cube root of it. So 8 times 8 is 64. And can you think of a number multiplied by itself 3 times that gives you 64? Turns out that 4 works. And if you're a little unsure of your arithmetic, just keep it the cube root, and we can write it as 8 times 8. And remember from the other example, it says if you can take the cube root of either of those numbers, pull it out front. I can think about there as being a times 1 in here as well. It won't change anything. Well, the cube root of 8 is 2, so I can get rid of that. The cube root of 8, I can pull out another 2. And then the cube root of 1 is just 1, so that would get rid of my cube root. And again, I have 2 times 2, which is 4. Probably another important example of doing a problem like this. Notice you can write 8 to the 2/3 power. I can write that as 8 to the 1/3 power squared using properties of exponents. Right, because if it's in parentheses, you multiply it. So this really says find the cube root of 8 and then square that number. So there's my square, there's my square. I'm just rewriting 8 to the 1/3 as the cube root of 8. And recall the cube root of 8 is 2, and 2 squared is 4. Okay, so kind of 3 different ways to go about getting an equivalent answer. If you're a little shaky with radicals, or maybe you're just learning them for the first time, I definitely encourage you to go through these examples and really convince yourself that you could do these anyway. Definitely very useful to kind of be able to manipulate radicals and exponential notation to get what you need. So when you see these fractional exponents, at least to me, really I'm thinking about them in terms of radicals, and that's how I make sense out of them. So this is the basic relationship between radical notation and fractional exponents, and there'll definitely be quite a few cases where you'll want to convert back and forth from one to the other. So I hope these basic examples make some sense. Again, they're not meant to cover, all the types of problems. They can certainly get a little more confusing, but this is the basic idea of radical notation and fractional exponents. Again, if you've forgotten some of your, maybe some of your factoring skills, or you need to get a refresher on fractional exponents, take a look at my website, justmathtutoring.com. There's definitely some free videos covering those topics as well. Definitely feel free to take a look at them, watch them as often as you like, and I hope they all help.